Okay. All right. Okay. It works. Uh, welcome. First of all, this is the first time I set up these things, so it took a little bit longer than I expected. Okay. So yeah. All right. I thought you were asking questions already. I like that because you put your hand up. Okay. Uh, let me introduce myself. Okay, I need this. Okay. Uh, I'm Qi Houduo. Okay. Uh, Qi is my family name. Uh, my research area is in optimization. You can say I can talk about anything about optimization. And this course is optimization for machine learning. The good thing for this course is this. There are so many resources online, different universities, different lectures that select different material to teach. All right. Uh, Optimization is already part of machine learning. Everybody needs to know something about it. All right. I thought about what I should cover for this course. You can see the problem is that we have so many topics, and I can only cover a small portion. My choice, probably all the algorithms and theory are covered. Probably they are big things in machine learning. Okay, they are widely used. Uh, Another difficulty is that I just don't want to introduce the algorithm, show how it works, and everybody can can go online and download some package and you can test by yourself. Therefore, my departure feature and departing point is that you will see proofs, theoretical proofs. But I spend a lot of time gathering the proofs that only use linear algebra and first year calculus. You don't use very advanced mathematical techniques in order to prove something wonderful, something great. Okay. So of course, all the good algorithms they have a magical part. Okay, what is the magic? Why you can discover such algorithm? Why can't I? All right, there must be a mysterious part. Okay, I will show you which part that you cannot do. Okay, I cannot do. Okay, it's only the author. Okay, the discovery that guy they can do. All right, because they are equipped with the expertise. All right. Traditionally, optimization was taught with coding. All right. I remember 10 years ago when I teach in a British university, when I taught in British university, and the first few lectures must be Python coding program, okay? Such things. Nowadays, Python programming is already a done deal, okay? You ask ChatGPT, you say, I got a great algorithm, please can you program for me? Instantly, they give you very nice program, all right? You will see the graphs, the result I produced, I presented in my talks, are all done by ChatGPT. All right. Previously, I coded it line by line by myself. All right. Nowadays, it's become so fast, so I don't need this part. Therefore, you are encouraged to test the algorithms I teach here. All right. Uh, you can see the performances. You can say why it is a big thing in machine learning. Why, behind the package, the black box, why these things works. Okay. I hope with such material, if you are equipped with such knowledge, in future, when some of you become a big, guy or big person in the machine learning area, or probably you set up your own company, and remember the theoretical things here you learn might be behind it. Okay, you cannot tell which part, but that is the difference between our graduate and any data analytical analyst, and that we know something about the theory. Okay, we know how to analyze algorithms, how we demonstrate it is effective, it works. Okay, so that is the background for the course. Okay, I hope you can check my proofs. I will give you a number of proofs. I will tell you which part is important, which part is not important. You can, and the standard is this: you should be able to understand the proofs, because it does not involve too advanced mathematics. All right, but appearance can be daunting, can be very complicated. But remember, our building block is big. Okay, previously, years ago, building block is small. All right, nowadays, even you ask school children, they play online, they play a lot of things which they don't understand at all. They play games, they don't understand at all. Why the game is so funny? Because the building block is big. So that is different from years ago. So building block is big. That's why our proofs, for example, theoretical analysis, looks like messy. Actually, if you look at the blocks, and it is easy. Okay, don't be afraid of checking those proofs. I know some of you are very strong in mathematics, and some of you are weak. Okay, we admit it. Doesn't matter if you don't understand. Okay, I got three very capable teaching assistant to help me to answer any questions you may have, because their expertise are also in optimization. The first one is Ouyang Ting. Can you stand up? And you can ask her any questions, especially tutorial. The second, Gu Endong, and the third one, Xu Yang. Okay, so the arrangement is this. I will teach 2 hours. Okay, so I haven't asked you whether you prefer to have a break between the 2 hours, or you want me continuously, teaching, lecturing. So what is your preference? Do you want to take a break in between teaching? All right. Okay, we can have a short break. All right. So that if you want to leave, you can still out. All right. You can leave. Don't force everybody to stay. If you say, okay, Professor Chi, I know this part. I'm expert at this part. I'm fine if you don't come to my lectures. But I believe I have unique things to sell to you. So I hope that you can stay in the class. Okay. Now this is the syllabus. The mathematical background, as I said, is numerical linear algebra. You can pick up any. Look, the point is that if you search online, I like the online material. If you search online, so linear algebra for machine learning, probably you got a good slides already there. So my use of linear algebra and really is fundamental. For example, it involves inner product, it involves norms, it involves cosine laws, is such things. It's not that advanced. So I'm going to talk about a few topics. So the first one, probably I plan to use 3 weeks to talk about what is called a first order method. First order method basically is called the gradient method. Okay, well, if you talk about to the expertise in machine learning part, they say, okay, we don't use gradient, we use automatic differentiation. Okay, that is AD. All right, but it is one kind of a differentiation, a gradient, because you will see the first example. You will see the functions is not differentiable. Okay, but everything you start from good things. So that is the gradient. So the first part I will talk about the gradient. Especially I'm going to talk about accelerated gradient. Okay, accelerated gradient method was used everywhere, especially in image processing. Everybody use camera, and when you do the denoising, the algorithm behind the denoising your photos, denoising your videos is probably this algorithm. Okay, accelerated gradient method, and also the proximal stochastic. Of course, the stochastic gradient method is behind machine learning algorithms. Okay, so we will see such things. Then I will talk about the second order method. You will say why we need the second order method, because it's fast. Okay, very fast. And the third topic, if you like statistics, if you have a strong statistical background, you would like it. It's called dimensionality reduction method. And that part, I will talk about my assignment. My assignment probably is coming from that part. Okay, so the last one is duality theory. So that is something probably is very first time when you see it, you probably is shocking. Why we need such things? Because everything, okay, has the other side. All right, the problem you have the front side. There's also back side. Okay, if you can solve the back side, you can solve the front side. There's always this one-to-one correspondence. So that is a wonderful theory behind those optimization. So I already mentioned the assessment. I considered it. I don't want 3 pieces. Okay, the 3 pieces usually is a midterm test, an assignment, and an exam. I got rid of the midterm test. Okay, the reason is this: I really want you to read something. All right, rather than solve artificially made problems. So I will give you assignment that count 30%. I'd like you to read, to investigate, to test. I will give you the method. I will give you the topics for you to work on. It is the individual assignment. It's not a group. Okay, so that you don't need to. So I found that the group project sometimes destroy friendship. All right. Probably you already have such experience. If you collaborate, if you collaborate, the collaboration goes well. You remain good friend for even more. All right. If the collaboration does not go well, right? Your friendship breaks down. All right. So we are going to have individual assignment. Then examination 70%. Okay, so you can see you must study the lecture material. All right, in order to get good marks. So that means you need to know a little bit of theoretical stuff and algorithms. Okay, so this is the rubrics, the boundaries, and this is the standard. Well, some of you already asked me, what are the references? All right. It's really difficult for me to give you one give you a single reference, a book about optimization for machine learning. There are already good books. For example, this one, patterns, predictions, actions, a story about machine learning. It's really a nice reading. There's online version. You can search it. It is about 300 plus pages. It's explained to you what is machine learning, why we need to learn it. It's good reading. Okay. It also involves some proofs. Without proofs, the author's point is that without proofs, you would never understand. You would never be able to appreciate what machine learning is about. Okay, you need mathematics. That is why everybody say we need mathematical foundation for machine learning. Why? Because mathematics explain what is to happen, what is not to happen. Okay, for certain. So there are good books. Traditionally, for example, this one, convex optimization, you will see why convex optimization is so important. So this 700 book is huge, okay? It's a huge book. A lot of topics is a reference book. But you can check, you can look at it if something is interesting to you. And the first one, numerical optimization, I saw the library got copies there. Really, that is above the third year or fourth year undergraduate student textbook. It's not hard. As I said, all it needed is linear algebra, differentiation, calculus, a very nice book. And both writers, Noether and Wright, they are famous mathematicians. And the first one, especially the second one, Wright, is this year's 1 hour speaker of International Congress of Mathematicians. Okay, so that is the biggest honor probably in mathematics. But he worked in optimization. Therefore, don't underestimate optimization. It's already, have a 1 hour speaker because the ICM, that International Congress of Mathematicians, that is only a few people can give a 1 hour talk, plenary talk. Everybody else is 45 minutes. So you heard a Chinese lady, Wang Hong. Everybody says she's going to win the Fields Medal this year and expect her to win, but she gives 45 minutes lecture. So you can say the caliber of the authors is already very high. And he also has a book about optimization for machine learning, but it's collected works. So that is it's not a book, it's collected works by different authors. Okay, so you can see there is a long paper here. So optimization method for large scale machine learning. So I don't, so that is my purpose. In my teaching, you will see, I give you everything. If I talk about a result, I give you a proof. Hoping you don't have to look into those big books. And also, I should mention this linear and nonlinear programming. This is a Chinese professor, Ye Yinyu. He works in Stanford University for many years, and he taught in Stanford University. Now he come back to China. Okay, he often, not long ago, he visited our department, and you can see those people even works in top university, even the ICM speakers. They all, treat optimization as a very important topic. So hopefully, so everybody can, be very serious. I know you come to Hong Kong Polytechnic University, you want to learn something. But if you want to learn something, learning something useful is not that straightforward. You have to put effort to it. Okay? Without effort, what is the worth of the master's degree? What is why you are here, right? So you are bound to meet some challenges. So I like you to you never know. Look, you may ask, why would I learn this? You never know. One day you may find it useful. Okay, and also you may appreciate why such algorithms they are they become so big. Okay, so let me start the our lectures. I hope is recording. Okay. This okay. You can see this is a gradient descent. Okay. So I like that we got a whiteboard. I'm going to use this whiteboard shortly. So everybody knows statistics is very important. Okay, even people say machine learning is statistics. You ask statisticians, machine learning, any topics machine learning treat have been treated by statisticians for centuries. Okay, so I like to use this Lasso problem to motivate really Lasso is behind the development of many things. And also, I'm not a statistician, but I can comment on it. If you ask statisticians, what is the most important advances over the past 40 or 50 years, 30, 40 years, okay? What is the most important advances in statistics? Okay, probably people say Lasso. All right. So, and one reason is that people joking say it got a good name, Lasso. Okay. So it is called least absolute shrinkage and selection operator. If you can understand every word of it, I mean mathematical meaning of behind this name, you are already expert. It's really a wonderful model. So where everybody knows least square, right? But absolute shrinkage, okay, takes a different meaning. And the selection operator, what is this? Okay, so is this this is regression. Okay. I suppose everybody has a statistical background, linear regression. So you have a data point, you have a beta, that is the coefficient, that's a linear function, the coefficient. So what do is you have observation BI, and then you want to treat the least square, right? And with this part, least square, we all know that least square solution. Everybody knows that. You can write formula for beta. If you don't know what I'm talking about, you should refer to your statistical book. This is probably the first year statistics. You should learn such things. Okay, linear regression. And what is really interesting is this is another term, lambda, and this beta. Beta is a vector, right? So beta is a vector. Okay, so probably you should try to see the beta is a vector. All right. And the beta norm, that is normal. L1 is called L1 norm. Well, I already say you use blocking your views. It's actually the absolute value of every component. Okay? Absolute value of every component. I think in tutorial questions, there will be something related to this. So if this lambda is a parameter, okay, is a tuning parameter, okay, or that's machine learning. What they do, they find the best lambda, okay. So you given a lot of data, you solve such a problem. Look, this one, first one is least square. Everybody like it because it's easy to deal with. It's a quadratic function. Okay. Remember in our school days, quadratic equation, quadratic formula, root formula, everybody knows that. Okay. So we like quadratic functions. That's why quadratic functions will appear everywhere. Okay, across disciplines. But the difficulty is that beta. Okay, everyone, look, this is the absolute value. Okay, what is the absolute value? All right, it's the ink is okay. The this absolute value is this very simple function. The two pieces on the left is linear, on the right is linear, but just in between 0. Okay, it is not differentiable. All right, on the right the derivative is 1. On the left the derivative is -1. But at 0, what is the derivative? If you refresh your first year calculus, right? When you define derivative, what is the derivative? You don't have a derivative, right? So derivative does not exist. Well, that is a call for a lot of techniques to deal with that point. Okay. So anyway, so you can see. So what I want to emphasize is this. You have a capital A point. This capital A point nowadays is billings. Okay? It's in terms of billings, not in terms of millions, in terms of billings data point. Okay? Think about you think about the XI. X is the data. What is data? Photo. You take a photo. All right? If you say I take a photo, look, how many people taking photos every day? And you can gather those data. They are all online. And you can see the scale of the data point in terms of 100 millions. Okay? But this is a big number. All right? But it has very good structure. Those data, they are separable. So you have one photo, I have one photo. It's not something your photo and my photo we joined together. All right? It is called separable structure. Okay? Machine learning, why machine learning works, why machine learning claim we can deal with billions variables, doesn't matter. All because it has a structure. Okay? The data is separable. Okay, that's a very important thing to remember. Otherwise, nobody can go that far. For example, you give me 10,000 data, I already dead. All right, I cannot run because the computer power cannot just deal with that. With a separable structure, we can do parallel computation. We can implement differently. We can use a lot of terminals to deal with data. So what is R? Regularization. Once again, such terms, I will use it frequently. Regularization. What is regularization? So this word. What is regularization? Why regularization important? Okay. So I like to give you why we need regularization. Okay. So I like it. There's a time here. Well, there's not equipped with pens. So I should bring my pen next time. So usually is equipped with pens. All right. So what is regularization? Suppose. All right. Suppose you have value 0. Okay. Suppose you have value 0. You have a function. Well, this. Well, this. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. 0. Oh, this is better, a little bit better. Look, suppose along the x-axis, okay, you have a constant, right? Constant is 0. The value is 0, which means you cannot tell which point is better. All right, they're all same because they take value 0. All right, so this is your function x equals 0. Look, y equals 0. Okay, this is the y-axis. This y equals 0. Okay, so y equals 0 for all x. Okay, for any x. Okay, that is the whole line horizontal. You cannot differentiate at any point. All right, but if I say, how about this? Okay, I don't need a absolute value. This could be my regularization function. If I add your original 0 to this quadratic function, it immediately give me the minimal value is 0, is here. All right? Okay, you would choose this point. Of course, if you want to choose a different point, you may add like this. Okay, you would choose B, right? So you see there's a selection, already there's a selection property there. So the regularization is very important in machine learning, okay? But of course, the word is wonderful. Why? It has so many regularization functions, all right? It's not just one. We have different people prefer different regularization functions, especially, for example, probably you don't feel it, but it's behind such things. Look, when you take a photo, use your phone, right? Sometimes your hand is wobbling, is shaking, all right? So the video or the photo take is blurring or is vibrating when you see it, right? So it happens to everybody. So these giant like Huawei, like Apple, what do? They they put something. Look at you look at your camera. The camera, the phone, the camera always stick out. All right, why is it stick out? Can you have you thought about it? Why the camera is out of is especially Huawei's phone, the camera stick out more than Apple's. All right, because they need to put a vibration reduction algorithm. That is a chip. You need to build a chip in your camera so that when you take your photo, the algorithm, that is the algorithm that is related to regularization, and smooth out your photo so that your photo is good. All right? But the real photo you took is really bad. All right? But it's because the camera has the function that reduce that what you call remove the noise. All right. Hopefully, in future, I may give you one or two examples to see such a functionality. And Huawei's camera stick out is because the algorithm they need to implement take more step, take more space, and with that, Huawei's photo quality sometimes is better than Apple's. All right, but Huawei is aiming to reduce that size of the camera. Okay, so we know this because a few weeks back, Huawei is giving us in the department give us a talk about this. Okay, we have a joint laboratory with Huawei and optimization laboratory with Huawei. That's the first one Huawei set up across the whole world. But there are other ones now. But the PolyU laboratory is the first one Huawei set up. Okay. So anyway, so you can see we have such a structure. I use this to have a structure, and I'm going to talk about gradient descent algorithm. Remember, this is L1, this is not differentiable, okay? So I'm going to talk about the real stuff now. I'm going to talk about, I have a function. You can always think this function is a Lassau function, okay? It's a Lassau function. I have a function. I want to find its optimal solution, okay? Remember, you might ask this question: why we care about optimal solution? Look, remember, we always want to optimize something. For example, I always I change my university to work because I want to have a better salary payment, right? When you do a job, you want to select a job that is close to your home and with good pay and with space to promote for promotion. So that's all things that we want to optimize. Okay, that's why without optimization, life is really boring. Everybody want to compete. Why you compete? Compete because compete for better. What is better? Optimization. Okay, everything. So I'm going to use C1. This is a standard. C1, that means once continuously differentiable. Okay, that means you can calculate the gradient. The gradient, I use this upside down this triangle. Okay, to say this gradient is the standard. For example, I have a quadratic function with two variables. You know, it is the obviously 0 is the optimal solution and give you the lowest value. But as I said, that real functions, real problems are not that easy. Okay. Okay. Also, you can anybody can interrupt me during my lecture if you don't understand. If you want to ask any question, okay. Don't be afraid of asking me questions. Okay. So what is the gradient descent? Okay. So you want, so the point is this. You want, okay, I randomly use this, for example, if you have a function like this, right? This is the function. I want to find this optimal solution here, okay? Suppose it's here. So you start from here. What do? You just want to go down, right? You don't increase the function value, you goes down. Okay, that's why it's called a descent. Okay, uh, which direction? Because it's multi-dimensional. It's which direction you follow. All right, so it says follow the gradient. Okay, where the gradient goes, you go. So what is the gradient? You look at the river. Where the river flows, that is the negative gradient. Okay, gradient flow. Okay, you think about, because it's a river, water always flow downwards. Okay, um, without any help. Right? If you have help, it can go upward. Of course. So the framework is very simple. Okay, this is a standard framework. It's not the only one, but it's the most popular one, dominant one. So you have a current point. Look, my notation is this. You have a current point xk, all right? And you have a gradient. Okay, suppose you calculate the gradient. Package now, machine learning packages, gradient is always black box. Okay, we don't need to worry about how you calculate gradient. Okay, that is why machine learning packages, they already tell you how to do this. Okay, so the algorithm is this: you follow. So from this point, you follow the negative gradient. I will tell you in a minute so why you follow negative gradient. And this alpha k is called a step length. How far you go? For example, I go this direction. It's a 1 step or 2 step or 1 meter or 10 meter. All right. This decide how far you go. Okay. You just update. All right. And the wonderful thing is that if you do that, sooner or later you get your optimal solution here. Okay. Of course, the whole theory is about what is the value of alpha k. That is the whole point. All right. The framework is clear, is simple. Current point, you can start any point, randomly pick a point, and you calculate the gradient, you follow the negative gradient, you decide how far you go, alpha k, all right? And you get the next point. The next point is closer to your target. For example, after your graduation, you found the first job. Your starting job is, my target starting point is 20K, right, per month. Okay, so but within 3 years, I like to get 40K or 50K, all right, and you need to move, all right. Otherwise, stay one place is very slow to get a higher salary. All right, that's why people move. Okay, so you can think about it this way. It's very logical. Okay, so it's this. So the whole lecture today is about choosing alpha k and give you some analysis. Guarantee that this xk plus 1 is better. Okay, we take a 10 minutes a break now. Is that all right? Okay. Okay. All right. Let's return. Okay. Um, so I forgot to mention, fortunately, some of you asked, the final exam is open book or closed book. You can see I'm serious. All right. It's a closed book, unfortunately. All right. Uh, uh, well, oh, that is something I want everybody to stay on for your tutorial. Okay. Uh, you see tutorial already put the solutions there. Okay. Don't look at the solution first. Okay. You got we got 3 teaching assistants here. You can always ask them and try to learn a bit by bit. Try to learn something. Okay. Uh, if you do well in your tutorial problems, you should not worry too much about the closed book exams. All right. Uh, so make use of the time, tutorial time. I know it's late, it's hungry, right? It's when people hungry, they don't want to learn. Uh, but that is the timetable, right? So it's a closed book exam, okay? Now, so I already explained this slide. Let's see whether it works, okay? This framework. First of all, we can get a better point, all right? So this GD is called a gradient descent, all right, GD, okay? So current point is fxk, and the next point you go this alpha, this step length or step size, okay? So you probably need to be careful with the word phrase I use. This alpha, I call it, sometimes I use is a step size, or sometimes I say step size. So step size sometimes is 1 word or 2 word, or step length. Okay, I see those the usage of those 3 words interchangeably by many people. So that refers to same thing, refers to alpha. Okay. So this is the Taylor expansion. This is the mean value theorem. All right. Mean value theorem is the most important theorem in calculus. Okay, so mean value theorem is not xy. All right, it's look. That's what I said. The point has a structure. The point is xk plus this. So this is the mean value theorem, and remember dk is a negative gradient. Okay, the negative gradient, and this part, the curly part, that part roughly equals this. Okay, this is the minus before it. Okay, it's roughly equals this part. Okay, so you can see use approximation. This is the gradient when alpha tilde. Okay, when alpha is small. All right, when alpha is small. So because your function is continuously differentiable, and this one approaches, and this one approaches the gradient, so that the quantity, this is the inner product. Look, once again, you should know the inner product is like this. Okay, it's what I call the inner product. Okay, and it's also sometimes called a dot product. Okay. It's basically x and y is x1, y1 plus this one. Okay. Okay, you multiply them together. You component wise multiplication. You add them together. This is dot product. So this is a quantity, right? This number approaches to this. You can see this is not 0, so this part is less than 0. So that's why I say this is less than 0. Therefore, the next point, the function value of the next point, we say current point is xk. This is the next point. So next point is beta. Why we say it's beta? Because we are minimizing. Our optimization problem is a minimization problem. Of course, if you have a maximization, it's different. Remember, maximization of the function, this is the maximization of function, is equals minimization of the opposite. Okay, so you can check. This is simple stuff. So really optimization you can only study minimization or maximization. There's no need that you study minimization and maximization, because one you can infer the other. Okay, it doesn't matter. So you can see when alpha is small, you can always have improvement every time. So you can think about it this way. I have a personal experience in terms of my salary increase. First year I got this much, next year a little bit more, little bit more, little bit more. Every year is a little bit more. But you think, or you always think, the small increment, okay? Small increase does not mean big, all right? So that's why you need to change your job. You need to get promoted. So once you get promoted, you get a big increase, okay? Big improvement, okay? So you can think about this one. You get the beta point in, I think in lecture 4, in 4th week. We will come back to this one, okay? So that means the function value is decreasing. That is good. But the point, as I said, where you are leading, okay? If you do this, where you are going, okay? If you know your destination, how fast you go, all right? That is something we always concern. We always think they are important. For example, you take a holiday, you go somewhere, you need to decide how I get there. Then you decide how fast I get there. All right? That is the both things are important for us. Okay? So the first thing is called convergence analysis, and the second one is called convergence rate. So how fast? So that there's talk about the speed. Okay? Convergence of the speed. Okay. Well, in order to answer such a question, you cannot grab a function, then you say, give you answer. No, 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 you can't. You have to restrict your function class, okay? For example, Lasso belong to this function class, okay? I start with the convex set, okay? Convex set is a very simple region, a simple body. So if you have a set, you pick up any 2 point between inside it, you draw a segment. All right, the segment is still inside. Okay, think about basketball. Okay, okay, the basketball, you draw any 2 point, you draw the line is still within the basketball. Okay, you cannot get out. Okay, so that is the convex body. That is good. Okay, even better, you think about your ice cream cone. Okay, everybody, I think the ladies like the ice cream. I like ice cream cone. Ice cream cone is a convex body. You think you visualize the ice cream cone, right? You think about this, all right? You think about, I use this. This is the ice cream cone, right? And you think you pick any 2 point. If you draw, it's within the body, within the cone. So this is called ice cream cone. It's everywhere. Or any ball games, or you know, the one thing, this classroom is convex, all right? If you draw anything, it's like a convex. But if you see that ship building over there, our fancy building over there, if you go inside the classroom, that classroom is not convex, it's curved. Okay, that's why people don't like it, because it's block a lot of things. Okay, block views. Anyway, so mathematically, it is very simple. So you pick 2 point x and y, you combine. This is called a convex combination. So that is linear algebra. Okay, you draw the 2 point, the segment. The segment, any point on the segment depends on the lambda. Lambda belong between 0 and 1. Okay, that is the algebraic representation. Geometrically, it is this. All right. So remember, when we learn mathematics, we learn 2 things: 1, algebra; 2, geometry. All right. The basic thing is you combine the 2, algebraic and geometry. Okay. So you can see. So this one is not convex. Okay. This one is not convex. Okay. There are a lot of convex bodies. Okay. With convex, you can also calculate, you can also define convex function. Previous definition is for points. Now it's for function. The function is this. If you draw, so let me explain this. For example, this one, this function, all right? I pick 2 points. This is x. This is y. I pick 2 points, all right? The function, this is the curve of the function. If I draw the segment, this point is fx, this point is fy, right? If you draw the segment between fx and fy, look, this is the segment, right? Refer to the previous slide. This is the segment. The segment, this one, is always above the curve. Okay, it's always above the curve. Such a function is called a convex function. And remember, this function, half squared or squared, is a convex function. But this function is not a convex function. X cubic is not a convex function. So because you can simply draw the cubic function, and this property is broken, is violated. Okay, so for optimization, convex function is really important. Okay, remember in my reference book, there is called convex optimization. That book is 700 more, 700 plus. It's nearly 800. It's a huge book. It's a very popular book. I can show you all engineering science student read that book. Okay, that book was used for Stanford University engineering master program. Okay, you can see. So you can see that is something why because I know the author. You can see the difference between very top university and the university. So Stanford University, obviously, is a very top university. Their master degree, you see how much they learn. Okay, the whole book, that's one module. All right, and you can see that book. There's also video there. It was made by the author. The video, the online video, is free for everybody. Okay, you can see the amount of material they learn, in my opinion, is significantly more than we teach. All right, but still, some of our students complain that we teach too much. Okay, that is not the point that I would agree. I would say, if you come here, every minute you should study. All right. You may not like this point of view, but we can always ask why I'm here. Right. Even for me, being professor, probably I don't need to work that hard. But I use every minute of my day. I do my work. So you know, that is a question about the existence, why we are here, right? So we are here to learn, we are here to contribute, okay? So the functions like this, the functions, you can see all the functions, square root function is not convex, but square root function, the minus square root function is convex. So I like you to see why, and also this one is a very special one. Delta C x. If x belong to C region, is 0. Otherwise, infinity. You think about you think about this table. Any point here is 0. After the point, boom, going blow up, infinity. Okay, that function is called indicate function. Okay, it's called indicate function. Very useful function. Okay. Engineers, computer scientists, they all like such functions. So you can see if C, this region is convex, the indicate function is also convex. Okay. As I said, the convex function alone is huge. All right, but we only use these simple properties. What is the simple property for the convex function? The convex function has you think about this quadratic function, x squared. X squared, this simple function has everything above the convex function. Okay? Has everything. So you can see, the first one is like this. You may question, look, that is the whole I always advise you how to learn mathematics. So really, this has already been taught in high school, okay? So any curve, right? Give me this is x. I can draw the tangent line. I can draw the tangent line, right? So everybody can calculate the tangent and it's norm, okay? It's normal line, okay? The high school, we already learned such things, okay? This tangent line, look, this is exactly the tangent line, okay? This part is already the tangent line. So convex function meaning given any point of the convex function, you draw a tangent line because that function is differentiable. You draw the tangent line. That tangent line is below the curve. Look, is that? The function is always bigger than tangent line. The x is fixed, right? And when y move around, okay, you can see that is the convex function. So this if and only if, that is a sufficient and necessary condition that a function give me a convex function, give me a point, I draw the tangent line, the whole function is above the tangent line. Okay? So that is a convex function. So we need this property. This property is essential. It's a very important property. And more than that, if the function, if a point is the optimal solution of your convex function, minimization function, the gradient must be 0. Okay? You think about the quadratic function, x squared. You think about the minimal point. The minimal point is 0. The gradient is 2x, right? It's x. X equals 0. That means the gradient is 0. Okay? So that's why I said quadratic function has everything that we need for the convex function. But you may ask, well, we don't believe you. Why you say the convex optimization is has a huge book, 700 more plus books. Why, if it's that simple, why we need that? Okay, that is the problem. Many functions are not differentiable. We are talking about differentiable functions. There are functions, many functions, differentiable. For example, determinant of a matrix, okay? Log determinant, okay? So there are many, complicated functions, okay? So look, the proof is really simple. You use a convexity, you use a convex function, okay? This is the definition of a convex function, all right? So that is bring to my point I initially made. The appearance looks like complicated. Actually, you are applying a basic definition to the function. It's, then you rearrange the terms, and then you divide by t, because t belongs 0 and 1 in the region, and you take the limit t going to 0, and we also, this is the definition of the gradient. Okay, if you learn the recall the calculus, this is the definition of gradient. Okay, so you can see this the quantity that we are interested in automatically is very easy to prove. Okay, that's what I said, that if the function is differentiable, it's easy to prove. If a function is not differentiable, for example, absolute value function, you cannot draw the tangent line at 0. Okay, it's not because that point is not differentiable. That is, I show you. I try not to introduce more advanced concept, but sooner or later I will touch a little bit non-differentiable functions because we need it. Absolute function is not differentiable, so you can see. And because of this, gradient equals 0. You can look at the proof. I don't know how many people have read this my slide before you come to my class. Have you read the lecture slides? Yeah, right. Good. I like to hear that. Yes. So that is the best way to do this, because if you have questions, you bring it to the class. If you don't want to ask me, ask my TA. Okay, they are more friendly than me. All right, so you can. They are, as I said, they are expert. You don't need to worry about. Probably they don't know. They know everything of such things. Okay, so yeah, you can see the proof is very simple. Okay, look, that is the thing that I like to emphasize. Okay. So if you watch toddlers, the little children, little child, okay, when they start to walk, all right, when they're at the one age, 1 year old or slightly 1 year old, they start work. As the parents, do you wish them to, work very fast? Okay. Certainly you don't. Any parents don't want the toddler to run. Okay. Why? If you run, it's not stable. Okay. You want stability. Everybody wants stability. For example, if you have a work, you want your job secured. Nobody can fire you. That is why university, for example, they cannot easily fire anybody. If they want to fire anybody, they need to pay. They need the compensation is very high. So we need a stability. But now think about the function. What is the stability of the function? Don't grow very fast. Don't change very fast. This is the Lipschitz function. Look, the function value, look at this. The function value, this is the change, the difference. The change is bounded by the change of the points. Okay? Remember this norm things is Euclidean norm. Okay, it's the L2 norm. It's Euclidean norm. It's a standard. It's a standard norm. I don't use fancy. I will use. So such norm is like this. It's a standard norm. No, okay. It's called Euclidean norm. Okay. So the whole point, the function class, I call the L Lipschitz, is this. The function value, the change of the function value is controlled, is well controlled by the change of the variables, by x, okay? So you don't want it to grow. In other words, you don't want your function to grow very fast or decrease very fast because that involve instability. And examples like this, they're all Lipschitz. And I think in the tutorial questions, they ask you to prove this. If the function is being Lipschitz, then its gradient is bounded. Remember, when we learn real analysis, okay, when we learn gradient, we don't want a gradient to be, going to infinity. We don't want a gradient to be very big, all right? When the gradient is very big, something bad thing happens. Remember 1 over x, okay? 1 over x, the gradient, you think when x is near 0, the going to infinity, that is the point that you want to avoid, okay? So that is the class of the function that we want to focus on. We want to focus on, it is Lipschitz, okay? The function is Lipschitz. Okay. If the function is Lipschitz, we can do something great. Okay. If we have a slow growing function, if I apply the GD algorithm, I can get good stuff. So I can get a point that is as close to the optimal solution as possible. So what is a good approximate solution? So I have a function. So this is a best value, right? If the best value, if I can find a point that is just less than the best value plus epsilon, okay, I'm satisfied. Think about this. Think about after your graduation, I always use salary as an example because, I need a salary, I need money. So everybody need money anyway. So for example, the first job within group, assume you are 20K, okay? But you also know the highest pay in your group is just 20K plus $1, and you would be satisfied. Okay, you say, okay, I'm very close to the optimal solution. All right, so that is approximate. All right, you want a point that is not too far from the optimal. We are satisfied. Okay, so that is. You may think, Professor Chi, why you emphasize such obvious things? The point is, machine learning just do that. Okay. Previously, optimization, we always want to find x star. We always want to find x equals 0. Okay. We want to find the best solution previously. And if you want to find the best one, for example, in our class, you want to be number one when you do your exam. You want to be absolutely number one. Think about how much effort you need to do. Okay, how much more effort you need to get to the very top. But if you say, I want to be top 3, I don't want to be top 1, number 1, I want top 3, or even I can want to be top 10. Look, immediately your work will be reduced in order to get there. Machine learning is always do this. They don't want to find the best solution. They want to find a solution close to optimal. That's why it's fast. Okay? I don't want to get to the top. I want to get near the top. You think this way. All right? So that is a philosophical change of the computation. Previously we always want the best. I want best. Okay? So we spend so much computational power to just get this small increase, okay, in terms of improvement, okay, and because the optimal solution is better, is best, why not? Well, that's why we are so slow. So when your problem is small, it is fine. Your computer is fast enough. But remember, our data now is in terms of 100 millions. Even you get this small improvement, you would spend millions of US dollars, okay, in order to do that. So the compromise is that I get what is called near optimal. Okay, that is a very important point. You want to get a near optimal point solution, not optimal solution. Okay, so that's why I introduce this definition. Okay, now this is this is the result. I'll give you the proof. So the result is this: if your function is differentiable, it's a good function. It does not change too much. Look, it's increase, it's changes every piece. Okay, and also it's convex. Okay, you think about this one. It's also convex. So let x star here to be the optimal, and you do the gradient descent. Look, this format is gradient descent with alpha, but my alpha is this. Okay, it's epsilon over L2 squared. Okay, this epsilon is very small. For example, epsilon is 10 to the power minus 4. Okay, you can see alpha is very small, and you update. So what you can get is this. In these many steps, okay, in these many steps, is D is the first point from, for example, this is your first point. Your first point to the optimal point, there's a distance, okay? You measure the distance. So the distance and d squared L over epsilon squared, you take that many steps. you will get the optimal, near optimal solution. This near, how close it is epsilon. Epsilon, as I said, epsilon can be 0.1, can be 10 to the power minus 4, depends on how accurate you want to get close to the optimal solution. The whole point is this. If you give me a tolerance, I can tell you how many steps you need to reach your target. Okay? You may think, okay, Professor Xi, you are not talking about nonsense, that why we need such things. Okay? Why would I tell you? Your mobile phone, everybody, you use a mobile phone. We use a mobile phone to compute. We use a mobile phone to communicate with me, and you receive calls, and you want sometimes you want the provider, for example, Huawei, want to say, okay, when your phone is ringing, okay, you pick up the phone, the signal coming, they want to say within millisecond, the signal should come in, okay? But your voice, everything you could get through the hardware, okay? There is a time limit for it. You cannot say 1 minute delay, okay? If you have a phone and the call coming, you have to wait 30 seconds. Even you wait 2 seconds, you would say, I don't want this mobile phone, right? So limited resources, okay? So that is all behind the computation. Those big companies, they need to say, okay, so this accuracy can be in terms of computing resources. It can be, for example, I'll give you a budget. The budget is this task. I'll give you budget $1,000. Okay, you need to get it done. So how much resources, how much iteration, computation you need to run? You need to estimate it. All right, and the estimation actually is implemented in the hardware. So it's closely related to such things. Don't underestimate. But so come back to our result. So you look at this. I'm not have to put the final point x capital T. I have to put the average of the point. That is another point. That's another machine learning the algorithm usually they average things. Okay, they give so much the effort to compute a lot of points, then the average is the point. So why average? That is the expectation already. Okay, so you see, this very interesting way to get your result. And the proof, look, the proof is not that hard. You use convexity. Remember, we just proved these convexity things, and then the gradient is different of the 2 points, okay? Because you update, you follow the gradient step, so that is a difference. Then you use cosine law. Remember, we have a Pythagoras theorem, a squared plus b squared equals c squared. That is for the right angle triangle. All right? If the triangle is not right angled, we have a cosine law, right? So that is, again, that is the secondary high school material. Then you just rearrange by the GD, okay? And you do this by the boundedness. Remember, the gradient is bounded, you get this. So it's really, the proof is not that the difficult. So you sum of it, you divide by t, and eventually you get this, all right? Okay, I'll leave it to you to check this. I checked, I didn't have any mistake over there. If you can find, if you can, I typed this, to my computer. So if you find any mistakes or typos, please let me know. Okay, so you get this one. Okay. Okay, so this is this is the first result. Okay, this is the first result we have. So remember, this result is not good. Okay, the reason I commented, the reason is that nobody uses this result. Okay, but it serves a good starting point. Look, how many steps t? So I have this t. How many steps? This denominator is epsilon squared. You think about the epsilon is 10 to the minus 10 to the power minus 4. All right. If you squared it, it's 10 to the minus to the power minus 8. All right. 10 to the power 8. All right. It's already more than 100 million. Okay. So there are so many steps. So that means it's slow. Okay? It's slow. And you may ask, you may wonder, well, why is it so slow? Look, you follow the gradient, the only culprit, the only issue here is your alpha. Okay? So that is why big companies, they hire so many people to try, what is the best alpha. Okay? That is one of the job to get this. So in order to do that, we have another class of function. And this should give us a better convergence rate. Okay? I call it arrow smooth. Okay? Arrow smooth. So what is the arrow smooth? Previously, is a function value that is controlled by the change of your variables. Now, is a gradient, the change of the gradient. Okay? The gradient, that they ask you, the gradient cannot change too much. Okay? You think about this. Gradient does not change too much. It's x. All right? If x changes a little bit, your gradient changes a little bit. Okay? Right? So this function, that's why this function is really good. Quadratic function. That's why that explains in high school we learned quadratic functions. I wished that I told my children that if I got a chance, I would love to teach high school mathematics, because I would tell them why you need to learn these quadratic equations, why you need to learn this, so I can give them a good motivations for that. And you can see we have a quadratic function. Function over there is just one variable. So this is a multivariable. So you can say L equals 2. And you can also see this is a quadratic function. So this A is a matrix. Okay? It's a matrix. You can see. And then this L is row A, that is okay, that is already type, that is the least absolute eigenvalue. So you calculate the eigenvalue. So this matrix is symmetric. We all know that from linear algebra, if a matrix is symmetric, it has real eigenvalues, and you can calculate the real eigenvalues, and you can choose the least absolute value. Okay, not least absolute value, is the largest. Oh, that is why is wrong. It's the largest. Okay? It's the largest. I will change that. It's the largest eigenvalue. It's called a spectral norm of A. If you don't like it, you can skip it. But it has a name. It's called a spectral norm of A. Okay? Right. This is for this class of function, for arrow smooth function, it has a very good property. It's called the descent lemma. Okay? So descent lemma is this. The function, you think about this. The function value can be bounded by a quadratic function. This is the quadratic function. If you look at this. So that's why I say when you read, when you learn, you need to see the bottom of the question. You need to see the point. doesn't matter what appearance it is. It is a quadratic function. You look at this. This is a linear term, right? You think about just one dimension. This is a linear term. This is the quadratic term. Of course, you fix x, right? You let y change. So that means the function is bounded by a quadratic function. Remember, we like a quadratic function. Anything that can be bounded related to the quadratic function, you probably got it right, okay? Quadratic function is fundamental. Look, for L smooth function, you can relate L smooth function to the quadratic function. So it's bounded by quadratic function. And this one, of course, is bounded by quadratic function because it itself is a quadratic function. Okay? Quadratic function is bounded by itself. Okay? So that means this function is L smooth. Okay? I can tell you L smooth. There are so many L smooth functions. All of them can be bounded by a quadratic function, depends on your L. Okay? Sometimes the L can be very large, sometimes it can be small. And the calculation, the proof, once again, is mean value theorem. Okay? It's not, once again, I skip it. I'll let you use the tutorial time to look at this. Now, for L smooth problem, I use gradient descent. Remember, my alpha now is 1 over L. Okay? It's 1 over L. Remember, L Lipschitz function, 1 L Lipschitz function, my alpha is what? It's epsilon over L squared. Remember, L can be very large. Okay? So you take a small step. For L smooth function, you can take a bigger step. So this is 1 over L. Okay? You can see it is 1 over L. Now, this is a very famous result. If you do that, the function value, this is the lowest. The F star is the lowest, okay? So Fk, this one, of course, is bigger than this one. This is a positive number. Here, on the left is positive. That means that measures how far you are from the optimal solution. And it's bounded by this. This is your initial point. It's bounded by L over 2K. K is the number of iterations, how many steps, how many gradient steps you take. Look, it is called 1 over K complexity. Okay, you can see I use capital O. In Taylor expansion, once again, I refer to the calculus. Taylor expansion, you always have a first order Taylor expansion, second order Taylor expansion. What is the remainder? All right. Remember, we have a remainder. Remainder is a capital O, all right, of the previous. You can look at it. This is the capital O. That means it's the order of 1 over K. It's like L over K. L can be 10, L can be 100, L can be million, but it's the order of 1 over K. Remember, this K can be very big. You can think about the modern computers. How many iterations you can get? Easily you can get millions, thousands, millions iterations. Doesn't matter. It's the CPU is so fast, and now it's GPU so fast. Okay, so you can see the whole point is that it's getting closer and closer. Is bounded by 1 over K. If K is 10,000, all right, it's already, the error is in the order 10 to the power minus 4. It's already very good. And this is called 1 over K complexity, okay? So that means if you run 100 steps, you get the accuracy 0.10%, 1% accuracy, okay? It's roughly, I'm not saying it's 1%, it's roughly 1% accuracy, okay? So that is the meaning of this result. Look, this is the proof. Probably, once again, you can see everything. What I like is I don't know the every time I teach this part, I always wonder why not me to prove such a result. Okay, it's not that difficult. It's already in the standard textbook. All right, everybody wanted to associate your name to a standard textbook result. Okay, if you do that, look, that is something. Once I asked the famous mathematician, I asked what you are proud of, and he said that when I die, I know something survived me for 100 years because my result is already in the textbook. So everybody learn it. Even I die, everybody learn it. They know it was me. So look, the proof is not that difficult. That's the whole point. I repeatedly say it's not. Let me give you this one, so you can interpret the new definition, new iterate in terms of this quadratic function minimization. Remember, previously, it is a minimization of a function, but now you are minimizing a quadratic function, okay? And then we all know that a quadratic function is convex. The optimal solution, look, the argmean, everybody should be familiar with such a notation. Argmean, that means the solution of the optimal solution is not an objective function. It's an argmean. If you use Python programming, you know argument, okay? The minimization, that means the point that minimize this function. So argmean, if you don't understand this notation, ask ChatGPT, okay? This is standard. So the gradient equals 0. We already said that for a convex function, at the optimal solution, the gradient equals 0. Okay? If you do that, you do the Taylor expansion of the function. This is the function. You do Taylor expansion at the different point. Okay? This is at the fx. You do the at different point. You have such calculation. The representation. This is 0, so you get rid of this. F is arrow smooth. It is bounded by the. It's bounded by a quadratic function. Look, this is arrow smooth. This function is bounded by the quadratic function of this. Then you expanded it. You cancel it. The whole point is that you can see the two terms. Okay, the two terms are adjacent to each other. Okay, adjacent to each other, and that means if you add them together, you have 2 because k can be 1, 2, 3, 4. You add them together, they're cancelled. So that is the technique. Okay, so exactly what they do it together. They add it. You can see everything come to this way. So once again, I like you while you are next time when you come to my class, spend 1 hour or 2 check my slides, because I always put on the slides at least 1 day before the lectures. You check that. If you don't understand, you can circle where you don't understand, then you can ask questions. So my requirement is that you understand the proofs. I'm not asking you reproducing the proofs. I ask you to understand the proofs so that you understand the algorithms, okay? So that's exactly, you add them together, you get this, all right? Okay. So let me show you. This is the gradient descent error. This is 1 over k. Look, this is what I told ChatGPT to do. Okay, I say, okay, I got a gradient method. I got a 1 over k complexity. Please demonstrate this algorithm, and they give me this. All right. So it's exactly, so this is the function error. You say it's get closer to the optimal because it's 10 to the minus 10 to the power minus 6. And in terms of k iterations, you can say it's here. So that's why there's a big difference there, is because it's above 1 over k complexity. So you take 100 steps. 1 over k complexity means probably you need to run 10,000 or 1,000. So it's order of 1 over k. It's not just 1 over k. Okay, it's order because it involves L, ellipsis, that's a constant. Okay. Consider now, before I finish my lecture, I like to give you a very nice function. And this function is very famous. I didn't tell you where I pick it. This function is very famous. We will see it in future. Okay. You may draw it by ask ChatGPT draw a graph of this function, but this function is famous. But if we look, this function is continuously differentiable. You can calculate each piece is quadratic. It has 3 pieces. Okay, this function has 3 pieces. Each piece you have a quadratic function, and the pieces are linked by first order smoothness. That means the gradient equal at the joint point. For example, at x equals 1, the gradient equals. Okay, that means the function joined and the first order agreement. Okay. So the gradient, you can calculate this, and then you apply the gradient descent algorithm. All right. So what do? You start from x0 equals 2. So you calculate the gradient, the negative gradient. I use the L equals 2, estimated L. You can see from the gradient, you can estimate L equals 2. You can update. Look, this is exactly the GD step. Okay, gradient descent step. I calculate this within 2 steps. Okay, I found the optimal solution. And I don't need to run 100 steps like the previous slides, okay? I run only 2 steps, okay? I get the optimal solution. This is called a finite termination. And this happens rarely. It only happens for quadratic functions, for nice functions, okay? But I just like you, because this finite termination sometimes is linked to deeper research like subspace. Okay, remember, good things lie in a subspace. Okay, so in future you will see, especially in dimensionality reduction part, you will see in this subspace you can have this finite termination property. All right, but I just like to show you, in addition to the convergence, take so many steps to converge, you also have a possibility that in terms of 100 steps, in terms of 2 steps, you reach the optimal solution. There are such possibilities. Okay, so such possibilities often appear in the subspace. Okay. Anyway, let me summarize what we have introduced, studied today. So I like to minimize a function fx, right? This is my problem, okay? Think about the lasso. At the moment, none of the algorithms can solve lasso, but you think about the lasso, okay? And I follow the GD, the gradient descent. The gradient descent is a very simple algorithm. Current point, you follow negative gradient, you go alpha that far, okay? So this alpha is step length. This is the search direction, okay? In future, we will have different search directions, okay? But at the moment, we use gradient. And you may ask why we need, since we have a gradient, why we need other directions? Well, think about this. Sometimes the gradient is hard, it's difficult to calculate. Okay, it's expensive to calculate. There are functions whose gradient you know is differentiable, but the gradient is hard to obtain. Okay, it's expensive to obtain. So that's why we need a replacement. That's for the future. Okay, so the framework is very easy, and this framework actually works for specific class of functions for L-Lipschitz. If for L-Lipschitz you choose alpha this size, and in this many steps, you get a good return. This average, this average return we will see it a lot of times, especially when we come to stochastic gradient. Okay, that's a very important part of this module. In week 3, I think we can see this is a very important part. I'm not after put xk plus 1. I'm after put the average of all the points. Okay, so that is a very important part for you to know. And for the L smooth part, alpha is 1 over L, and the complexity now is 1 over K. All right, so you can have this in this many steps. Look, you can translate this result to this. In this many steps, you can reach the epsilon optimal solution. So this is a near optimal solution. Remember, L-Lipschitz function class, this is epsilon squared. Okay, but for L smooth, this is epsilon. Remember, epsilon is a very small number. That means for L smooth class of function, you use way less number of iterations. Okay, and you get this. The iteration is this. All right, this should be 16 rather than 8. Okay, I doubled it. This should 10 to the power 16. All right, so you can see for this one, for alpha, you use 1 over L. You use 10,000 steps. You get a good near optimal solution. But if you use 1 over L squared step length, that means every time you take a very small step, right? You see, you take many steps to reach that far. But if I take this step, right, I can go quickly. But the point is, how do you know which step you take? All right? So then we need to focus on different class of functions. So for this, you may ask, okay, 1 over K, can we have a better one? Right? Next week, I will tell you a result. That was probably celebrated result. There's a wonderful story behind it. So there's a better result for this. Okay, that is the job of next week. I think I already overrun 10 minutes. But anyway, the next hour, I will hand over to my 3 TA If you have any question, they are here and to help you explain everything. If you want to talk to me, all right, if you want to ask something deeper or anything, you can drop me email or you can come to my office, make appointment. I'm happy to answer any question that is related to this module. I hope that this module can at least introduce you something that you don't know already. Because nowadays you got ChatGPT, you got everything, you can learn very fast. You can learn a lot of things. But I hope that I can explain to you what is behind those algorithms. Okay, you can take a break. Then as I said, the next hour is for tutorial. You got 6 questions. You can stay on and ask my helpers. So before we have a break, any comment, any question, or any suggestions you want me to change? You want me to? Do you have any question, comment? How for how I teach my lectures, how I give the materials? So I'm open. You can see I'm open. As I said, my purpose is that I like, to introduce you something that is new to you that you would not be able to learn from elsewhere. Okay, so if I can do that, I'm satisfied with my, preparation, selection of material. So that is my purpose. Okay, so if you have anyway, I repeat, if you have any suggestion, you can. If you don't want to tell me now, you can drop me email. You can, uh, the purpose is that we learn something new. Okay, okay, we can take a break.